Okay, here we go. So the question says to solve this system by graphing. So first of all, we just want to make sure we understand what a system is. It's the same idea that if you could certainly get a lot of these problems right without really understanding what the thing is. But as soon as you bump into something that's a little bit unusual or tricky, all of a sudden you may be really lost at sea, right? Whereas if you understand what the problem really is, what it's asking you to do, then hopefully when you see something that's a little unusual, you're able to stretch and get to that idea too. So these are both lines, right? These are linear equations. If you take college algebra, you will see some nonlinear systems, but these are both lines, right? And we know, in fact, what those lines look like. And when I say what the line looks like, we know that really means the solutions to that line. So y equals minus 2x, that's a line that has a y-intercept of 0 and a slope of minus 2. So I'm going to start there. The slope of minus 2 means I go down 2 and over 1. Get a line that looks like that. So remember that line is a whole bunch of ordered pairs, and each of those ordered pairs makes this top equation true. Okay, that's the work we did before with lines. This is also a line. I could graph it. I could plot points. That's certainly a fine way to graph lines, but I can also rearrange this one because I like to use the slope and the y-intercept, right? So 3x minus 1 is there. Minus 3x means I go down 3 and over 1. And I get a line that looks something like this. Now, this line here, right, represents all the solutions to this equation. So any point on this second line is going to solve this equation. And the system means I want to solve both of the equations at the same time. And so I think with that understanding, it's quite clear kind of what the point we want is, at least the idea of it. It's well, then this is the problem with graphing, right? It's like wherever this graph crosses one another, maybe it's there. It's not a great graph, right? Maybe I should have sharpened my pencil a little more before I started. So this is the solution that we're looking for. So the question is, what point actually is that solution? And this is the problem with graphing. It gives us a good idea of what's going on. I can see the solution. It does not give me a very accurate way of actually finding what that solution is. So that's where we want to introduce some algebraic methods. And I would actually encourage you to sort of ignore the book's instructions on these. The graphing is important to visualize it, but it's really not a good way to solve the systems in general because of this problem, right? Like I ended up with a bad graph, but even if it was a good graph, it's not clear where that point is exactly, right? I don't know. So let's introduce our kind of other methods of solving, our algebraic methods of solving. And we have two methods: substitution and elimination, which is also called the addition method. So these are two algebraic tools for solving systems. And it turns out with linear systems, either one of these will solve any linear system in two variables. So you really don't need both of them. But there's a lot of situations where one method is a lot easier than the other method. So we do want to know both of those because, well, we like things to be easy for one, and we want to be able to choose the proper method when needed. I won't force you to do one method or the other. So if you decide, I'm only going to use substitution, you can do it and you'll get full credit, but you'll definitely be making your life a lot harder on some of the problems. So the idea of substitution is that if I just have an X and a Y in the problem, I actually have infinitely many solutions, right? And I can see that here from my graph, right? There's infinitely many points that give me a solution. So that's not super helpful. Too many solutions, right? Don't give us what we're really looking for, which is this single solution. So the goal really in both of these methods is to combine the two equations so that I get rid of one of the variables. That'll give me a way of solving and finding this one single solution to that new equation. And the way you do it is different depending on the type of technique you're using. So in substitution, what I'm going to do is take one of the equations and replace the variable using this equality, right? Y is equal to minus 2x. So substitution says I can take those and sort of put them together to get 3x, and instead of y, I'm going to substitute minus 2x equals minus 1, right? So instead of y, I replaced it with minus 2x. So 3x minus 2x is x, and I get x equals minus 1. So that was pretty easy to solve, right? Once I put in that replacement. Now the problem is I actually haven't found the solution, because just like both of these linear equations, the solution is an x and a y. All right, so I found the x, but I need an x and a y. Luckily, for both of these equations, if I put in x equals minus 1, I should get the same y value, because this point is on both of the lines, right? So no matter what x it is, if it really is the solution, it's going to give me the same y for both of these equations. So typically, we just encourage you to pick the simplest one. Y equals minus 2x is certainly the simplest one. So y equals 2. If for some reason you wanted to choose the other one, which is totally fine, 3x plus y equals minus 1, that would be 3 times minus 1 plus y equals minus 1. Minus 3 plus y equals minus 1. And when I add the 3 over, I get the y equals, oops, sorry, I'm off my page there. I get the y equals 2. So my solution is then the point minus 1, 2. All right. So the other strategy is elimination or addition. And the idea here is that rather than doing the substitution, I got a little bit lucky with the substitution because the equation was written y equals something. So it was easy to replace the y value with that something. This was a very good candidate for substitution. But if like x and y were kind of mixed up together, it could be a little bit of work to figure out what y equals if I wanted to make a substitution. So that's one of the weaknesses of substitution. It actually is more likely to generate fractions. And, I know how we all feel about fractions, right? We would like to avoid them. Elimination is a little bit better at avoiding fractions. But you also have to kind of make sure things say, fit together. So what I'm going to do here to do my elimination is I'm going to move the 2x over to make it plus 2x plus y equals 0. And my other equation, I'm going to think of 3x plus y equals minus 1. So when I'm doing elimination or addition, I like to have all my x's and all my y's, and then an equal sign, and then the numbers all lined up. Now, I could, it is true, add these two equations together, and I get a true statement. That's a fact of equations. However, my new equation would still have x's and y's. So it turns out it wouldn't be very helpful for me. The way I can fix that here is I can multiply this top equation by a -1. As long as I do it to both sides, it doesn't change the equation. Now, when I add these two equations together, the plus y and the minus y will cancel. That's why I chose the -1, because I was anticipating that that would cancel. Minus 2x plus 3x is x. However many x's I get is fine. And whatever my constant is fine. But I cannot have, in this case, y's. It's also fine to try and cancel the x's, right? But I've got to cancel one of them so that I can find the solution. Right? X equals -1. Just like before, we're going to sub that -1 back into one of these equations to find our y value, right? Not surprisingly, we're going to end up with that same solution. Those are our two methods, and that's really is kind of the strategy. Now they can get a little messier sometimes if there's, like I said, some fractions or some larger numbers involved, but fundamentally that is the approach for both of those. Are there questions about any of these methods? Notice the solution here. My graph wasn't great, but it certainly seems plausible that my solution is -1, 2. I mean, it's certainly not what I would guess just from looking at it, but oh, sorry, it doesn't look very good because my y-axis is kind of crooked there, right? I started off with a bad axis and everything else went sort of haywire. So apologize for that, but maybe that's a good learning tool as well. Questions about any of those problems? Any other homework questions that you have that you know of? Okay. Let me give you one more example here. Let's try. Sorry. Okay, here's another system. again, we don't actually want to do graphing here, right? We want to imagine in our heads that there's two lines and they may cross, which would give us a solution. But as we saw from the last problem, that graphing, it's not necessarily going to tell me what that solution is. So I want to do an algebraic method. I could do substitution or I could do elimination. If I'm going to do substitution, then I have to solve for one of the variables. So I need to get x equals or y equals. I can do either one. The problem is I'm not really looking forward to doing that. I certainly can, right? I can rearrange this top equation to get y equals. We've done that with y equals mx plus b quite a bit. But I know that's going to generate fractions because I'm going to have to divide eventually by this -3. And those fractions are going to go into this problem. Not our favorite. The bottom one is going to be a little easier to solve probably for x or y, but again, you may avoid fractions, but it's definitely some work to solve these. So I would say substitution is not perfect for this problem. Elimination is not quite perfect either though, right? Because if I just add the two equations together, neither of these cancel. Right, so that doesn't work. So in that case, you can do either method, but I think this one's pretty good for elimination, even though it's not perfect, because it's not going to take too much to make one of the variables cancel when I add them together. And the one to do that with is certainly this, right? Because all it takes is to multiply by -2, and these will cancel. So I'm going to multiply this whole equation by -2. -4x minus 8y equals -16. I'm just going to write the other equation next to it. These are ones where you don't want to skip steps. You want to really take care and not make any small errors, right? It's sort of a disaster to make a small error. So when I add these together, because I multiplied by -2, I was able to match these up perfectly. So when I add those cancel, -3y minus 8y is -11y. -11. So y equals 1. And now I know I've got really my solution. I have the y value in my solution. So to find the x, I just need to plug it in. I could plug it into either one of these equations, but I like the bottom one better, I think. Two x plus 4 equals 8. 2x equals 4. Right, when I subtract the 4 and when I divide by 2, I get x equals 2. I'm okay if you just circle that, but technically, right, the solution is the x and the y together. So an ordered pair is kind of a nicer way of writing that. Any questions?
Where did you get that -2 again?
Yes, so that is kind of the key. I chose it because I wanted to cancel these x's. And I saw by multiplying by -2, this is going to give me a -4, and those are going to cancel. Everything else just kind of comes along. I'm not paying any attention to what happens in the beginning, right, with the 4y and the 8. They have to get multiplied by -2, but it just happens. I'm concentrating on this because I decided I wanted to cancel the x's. That one seemed easiest to me. Other questions or
Can I move on to the next problem?
sure.
From section 3, homework 3, question 6.
Yeah, great. So what happens is then in section 3, you do some application problems with that involve systems. Sorry, question 6, did you say?
Yeah.
So just like we did application questions before, you want to be very clear about defining your variables, and you want to be very clear about setting up your equations. All of those same application steps hold. The difference is here we are going to have two variables, an x and a y. And then when we try and solve that, that's going to then have a system that we're going to solve. So if you're going to define two variables, an x and a y, you need to have two equations in order to come up with a solution. So we kind of like to stay away from two variables unless it makes sense with the problem. So what it says here, a first number plus twice a second number is 5. Twice the first number plus the second totals 31. Find the numbers. So it's an application problem, but it's an application problem right in words. So I've got to decipher those words. But there's the unknowns here are there's two numbers. So I'm going to let x equal the first and y equal the second. Right, those are the two things I want to know and that I'm told about in the problem. Okay, so a first number plus twice a second number. So a first number, x, plus twice a second number is 5. You got to translate it correctly, or of course you won't be able to solve it, or you won't be able to get the answers, right? Unless you have the right statement here. Twice the first number plus the second totals, this is the way of saying equals, 31. So in order for x and y to meet these equations, they have to solve both of those, right? X and y are the first and second numbers, so they have to match these equations. And that's always with applications, that's kind of our goal, right? Is to take the words and then change those words into equations, right? And we're actually better with solving equations than we are, with the words. So with this one, I think you'd be relatively well suited to use either of our methods, substitution or elimination. For variety, I'll do substitution here. When I'm doing substitution, I have to pick one variable to solve for somewhere in the problem. There's two really good candidates. I could solve for x or y. If I tried to solve for y here, I'm going to generate some fractions, right, when I divide by 2, and so I don't want to do that. But solving for x is nice. If I subtract the 2y, I get x equals minus 2y plus 5. So that value is going to go in there for x. Be very careful with your positives and your negatives. Any mistake, right, kind of messes up the whole problem. So I add those together and I get minus 3y. I subtract the 10. That gives me 21. So y equals minus 7. Just like before, I need to find my x value here. This is one of the nice things about substitution is that it gives you a really nice equation to plug into, right, to find the other value. So that's 14 plus 5 or 19. Any questions on that one?
So you were saying that if you chose the y, the 2y equation instead of the other one, you'd get fractions. So exactly how would we know that we would get fractions?
So, well, you'd find out when you did it, right? And then you'd say, oh, and sometimes you can't avoid it. Sometimes if you're doing substitution, like with this previous problem, no matter what I solve for, I have to divide, right? Like to solve for x, I'm going to have to divide everything by 4. So that's going to create 3/4 and 5/4. Those are fractions, right? And then when I plug it in, I'm going to have to then multiply that all by 2, and those get sort of heavy operations. So here, right, to solve for y, I'm noticing that I'd have to divide by 2 at some point, and then I'd get a 1/2 x and a 5/2. Not the end of the world, right? But I'd rather avoid those if possible. Does that help?
Yeah.
Okay, it's an excellent question because that really is kind of the key thing here is like, well, how do you know which kind of steps or which route to go, right? And once you do a couple of them, you'll start to get a sense of what's going to happen, right, as you work through them. In the beginning, you're kind of running blind a little bit, right? But it does become clear. And again, there's nothing wrong with working with fractions, right? If you need to, you do, and you guys can often do just fine. But since we have the choice, right, we'd like to choose what's going to be easiest for us with these. Okay. All right. So the other thing that you're going to have to see how many of these I have. Looking through the homework, I don't think I have a ton of those. So the two other things that we haven't run across yet are where we have no solutions or infinite solutions. So remember, graphically, each of these equations is generating a line, right? And so we've seen or can imagine that those lines cross, which give us a solution. But it's also possible that the lines never cross, right? That they're parallel lines. And so then there would be no solution to that system. And it's also possible that the two lines really fall right on top of each other. And so every point on that line is going to end up being a solution. So those are two kind of special cases, I guess, or edge cases. And they're easy to see if you have the graphs relatively, but hard to see. Well, you have to do a little work to see them from algebra, right? So what happens is if the lines are parallel, they have the same slope. So here would be two equations or a system. If I tried to solve the system, I think you could see that if I solve this for y and this for y, I'm going to get the same slope. I'm going to get the same coefficient on x when I write it as y equals mx plus b. And I'm going to move the 3x over and divide everything by 2. Right, and I get this. That's my first equation. If I do the same with the second equation, divide it all by 2. Oops, 9/2. So if I'm given it like this, I can see this algebraically because these have the same slope, but they have different y-intercept values. So those are going to be parallel lines that are never going to meet and have a solution. So this is going to be no solution. You can also write that as with a circle and a line through it. Right? That's no solution. Now, it's not always quite so clear in the beginning if that's really a no solution. What happens is if you try and solve this using, say, the elimination method, I'm going to multiply through by a -1. And when I add those together, the y's and the x's both cancel. And I end up with 0 equals -3. And what that's telling me is that this is always false. Right? And that means no solution. I cannot leave my answer like this. That's not telling me what the solutions are, right? That's just sort of saying something that's obviously not true, right? You need to answer the question, you need to actually say what the solutions are, which in this case, right, are no solutions. The other scenario, it does appear to be similar. It's where you have these sort of matched values. But in this case, both the lines are actually the same line. Now, it will not always be, again, quite so obvious. There are some ways of sort of disguising the two lines, so it's a little hard to tell that they really are the same line. But when they're the same line, and again, you try and do elimination here, the x's and the y's cancel, but so does the constant terms, and I end up with 0 equals 0. This is a true statement. And that means that every point on one of the lines is a solution. Now, it's a little trickier to write that. We can't just say all solutions because it's not every point that works. It's only points on the line that work. So the way we have to write that, and the book will kind of give you a template for that. But this is actually the solution we're looking for. And what that really is saying is that the solution is all ordered pairs so that 2y plus 3x equals 6. That's just saying, this is a way of saying every ordered pair that's on the line is a solution because those two lines overlap each other. So any point on one of the lines is going to end up being a solution to the whole system. It's going to solve both of the equations. So when the x's and the y's cancel, you're either in one of these two cases. If it's a true statement, it could be 6 equals 6 or 2 equals 2. That means you have infinitely many solutions. If it's a false statement, whatever it ends up being, that means you have no solution. So those are two special cases that happen when the lines have that kind of special relationship, parallel or the same line. Okay. Any other questions from systems? Okay. So the first 3 homework assignments are all on systems, right? Different types of solving systems for the first 2, and then some applications of systems for the last one. And then we switch gears for the second half, which is about polynomials. And it's chapter 5 in the book, polynomials. And we work through some exponent rules, and then we work kind of adding and multiplying, kind of doing some basic manipulation with polynomials. So I'm going to talk about exponents today, which is both the 4th homework and the 7th homework are both about exponents. And then 5 and 6 are about working with polynomials. So we can talk more about those next week, as well as your other questions. So in the exponent section, what we want to do is learn how to work with expressions that involve exponents directly. So what I mean by that is, you know, we know or should know what 2 cubed is, right? The cube means I'm multiplying 2 by itself 3 times. 2 is the base. That's the power. And when we expand it, expanded form, right, we can do that multiplication and end up with a number, right, like 8. So we can always do that with numbers, but of course it can be very awkward when you have a really big number, like 5 to the 7th. It's awkward and hard to work with if you expand it out or multiply it out, but it's very compact to keep it as an exponent. So there's a lot of situations where we really prefer the exponential form versus this kind of expanded form, or what the value is. And our goal here is to be able to work directly with those exponential expressions. In order to do that, we need some rules. So we're just going to kind of list out these rules and give us a general game plan for simplifying these exponential expressions. So number 1, the rule says a to the n times a to the m equals a to the n plus m. So what that says is if the bases are the same, I get to add the exponents together to get my new exponent. That's the way we do multiplication with exponents. I do not multiply the bases together. I only keep track of the multiplication using the exponents. So for example, 2 to the 5th times 2 to the 7th. Those have the same base, so I get to add the exponents together. That gives me 2 to the 12th. And it's not really a surprise, right? Because we imagine, right, 2 to the 5th is 5 2s, 1, 2, 3, 4, 5, and 2 to the 7th is 7 2s. And so if you lined them all up, you get 12 2s. That's all that rule is saying. Right? But it's certainly much nicer than actually writing out all those 2s and counting them, right? That sounds unpleasant to me. Our second rule has to do when we have a power raised to another power. And it turns out what we do is we multiply those exponents together. I'll tell you, these 2 are the most commonly mistaken rules that we have. People mix those up all the time. They multiply exponents when they should add exponents and vice versa. So do be careful because you'll get a very different result, right? If you add versus when you multiply. So 2 to the 5th to the 7th. This 7th is actually saying I get 2 to the 5th 7 times. And if I added all those 5s together, 7 5s, that's multiplication. That's going to give me 2 to the 35th. That's a gigantic number, right? But easy to write as an exponent. Any questions so far? Okay. The next two rules are very similar to each other. I would kind of like to group them together, but the book usually keeps them apart. It just says when you have a product or a quotient, so multiplication or division, and then an exponent, that you can actually apply the exponent to both of those pieces. Doesn't work with addition or subtraction, but it works with multiplication and division. For example, 2x to the third. Well, that's 2x times 2x times 2x, so I end up with 3 2's and 3 x's, right? And that's what that rule is telling us. If I'm subtracting exponents, that comes from division. And, you know, I actually don't think this is crazy. If you multiply two things together, we add the exponents. So if we divide two things, it actually feels like that should be subtraction. 2 to the 6th over 2 to the 4th. What really happens here is I cancel 4. There's 4 2's on the bottom and 6 2's on the top. 5 6. And so we're canceling those 4 2's, which leaves me 2 squared, right? 6 minus 4. I don't want to write that out each time, right? I want to be able to know that it's 2 squared. And the order here might be slightly differently than the book. So in the beginning, they won't, I don't think, show you negative exponents, but that comes later. A negative exponent, remember, a regular exponent means multiplication. 2 times 2 times 2. So what's the opposite of that? That's what a negative is the opposite. The opposite of multiplying something together 3 times, it turns out, is really dividing it that many times. So a negative exponent is actually expressing division. 3 to the minus 2 is 1 over 3 squared, or 1/9. It's not positive or negative numbers. It is just division, which is really moving that term down to the bottom. So the negative exponent, when it goes down to the bottom, becomes a positive exponent. That's sort of the functional way of looking at it. Like, it's not the meaning. The meaning is division, but effectively that's moving things to the denominator, the bottom. Okay. There is a sort of final kind of special case. A to the 0 is 1. So I don't know, this one feels differently than the other rules, but anything to the 0 power, it turns out, is equal to 1. You can watch the video if you want a little explanation of why that's true. But it's fine to just think of that as a rule. Okay, so you should be asking yourself, what do I do with all of these fancy new rules? And I'll tell you, your goal is to simplify. And when you are simplifying, you are trying to do three things. And if you keep these three things and accomplish these three things, you'll have accomplished your problem. Number one is we want to remove parentheses. Okay. So when I look back at my rules here, I can see rule number 2 and 3 and 4 all take expressions that have parentheses and turn them into things that don't have parentheses. So these are simpler than what I started with. Okay. So those are the rules to get rid of the parentheses. Number 2, we want to combine what I call the like bases. So if you have a problem, you shouldn't have an x and another x to some powers. You should combine those into one x into some power. And so looking at our rules here, number 1 certainly does that, right? It takes 2a to the powers and combines them into a single power. It also happens here in number 5, right? I have an a on the top and the bottom, but that gets combined into a single a. This is certainly simpler than this. And at the end, after you've accomplished all of that, and again, this won't happen until the last homework assignment, but you want to eliminate negative exponents. I don't want to have an answer with negative exponents in it that is harder for me to work with. It's a little more confusing about what it means. I always prefer a positive exponent. Okay. So I'll just give you, maybe 2 examples here, and then that's a pretty good round for tonight. Let's try this. So we're trying to simplify. So I'm going to follow these rules here. I'm going to first remove the parentheses. I'm going to do that by applying that exponent to both of those pieces. That was one of my rules to get rid of the parentheses. And when I have x squared to the 3rd, I multiply those exponents. That was I think our second rule. So that gives me x to the 6th. In the bottom, if there's nothing written, you assume that's a 1. X to the 1 times x to the 4th. In that case, I add those exponents. That gives me x to the 5th. So I guess I moved ahead there, right? I removed parentheses, but I'm also starting to combine the like bases. So I don't want x's around here and here and here. I want to combine those to a single x. So these 2 on the bottom became x to the 5th. Here I'm going to subtract the exponent. X to the 6 minus 5 is 1. And this is a good answer. If you want to, you can write that out as 8x. But this also meets all of our requirements. Let's try x to the minus 2, y to the 3rd to the 4th over x squared, y to the minus 5. So the negative exponents, I'm not going to worry about those till the very end. I'm just going to continue on. I have to keep track that it's a negative number, but I can do all of my same rules. I'm going to apply this exponent to both of these, and I'm going to multiply. So that's going to give me minus 8 y to the 12th. No more parentheses. That's great. Now I'm going to combine these x's together and these y's together. And it turns out when you've got positive and negative exponents like this, the way to think about it is if I move this piece down to the bottom, I change the sign of the exponent. That's really what this rule is, number 6 here, is telling me. I didn't write that with a 1, but I could have. So moving it down to the bottom makes it a positive. So just focusing on the x's here, I'm going to get x to the 8th, x squared, y to the minus 5th, moving that x to the minus 8 down. And then those, of course, are going to give me x to the 10th. I can do the same thing, it turns out, with the y's. I could move this down and make this a minus 12 in the bottom, but then I'd be making it like more negative. I want to make it positive. It turns out by moving it up, I also change the sign. So if you flip the position, you change the sign of the exponent. The x to the 10th stays down here, but this minus 5 comes up as a plus 5. And I'm going to end up with y to the 17th. So again, if you haven't seen those or worked with those at all, that may feel a little, well, I don't know for sure, but it could feel like you don't know all those things that are going on. But look back at this if you need to, and you'll see some skills. There's definitely more examples, very similar examples done in the D2L videos as well. Any questions on either of these problems? Okay.